All right. Thank you. Turn it on for me.
Just hold it. Okay, can you hear me? Okay. Okay. So the time is limited, but I will try to present my work, and after that you guys can rush to the restaurant for lunch. So today I'm going to present the work Scrap Your Boilerplate with Object Algebras. I'm Haoyuan Zhang from the University of Hong Kong, and this is joint work from with Zoe Chu, Bruno Oliveira, and Tej Svenderstone. And so I'll give the problem first, the motivation. So usually sometimes when we write programs, we need to deal with abstract syntax trees, and usually there is some so-called boilerplate code in this AST traversals. So there are various operations that use similar code. So an example would be we deal with a data structure, for example, an arithmetic expression, and we need to collect the free variables in this expression. And when we have some other operations, so sometimes we have some similar code, and writing this similar code can be very tedious. So how can we avoid this boilerplate code? So I will show you our approach, and it can be rather painful with some large languages with many different types of nodes. So that's a problem. And actually there is a lot of related work. For example, the adaptive OOP and strategy programming and the visitor pattern and some other visitors, and also traversals in functional programming. But it's it's a bit hard for one approach to integrate all the features. For example, is the approach type safe, and is it extensible, and so some other feature, is it efficient, some features. So it's hard for an approach to have all these features. So later, our contributions are we capture a number of design patterns for various types of traversals in abstract syntax trees using object algebras. And then we provide a plain Java library called Shai. This Shai framework uses Java annotations, uses Java reflection to generate this kind of boilerplate code and automate the traversal design patterns. And the features of our approach are the approach is adaptive to further changes, and it's structure shy. So the structure shyness means the design and of data variants and the behaviors are separated. So it's structure shy, and it's also extensible. Later we will see it's extensible on 2 dimensions, and it's type safe based on the Java type system, and it also supports separate compilation. And then there are a number of applications and our case study. So here is a simple example that's an arithmetic expression. So this is the data structure of this example. So we have the expression, and there are 3 data variants: the literals with the integer as the input, and the variables with the string as the input, and also the addition of another two subnodes, 2 small expressions. So usually when there are some, we need to deal with some operations, we need to traverse this syntax tree, and what would be an operation? So we have these queries. This name is also used in some other, in many other papers of this field. So a query takes an abstract syntax tree as the input and gives a result. So for example, this expression is, as you can see, it's 2 plus x plus y, and an operation can be, a query can be, we collect the free variables inside. Actually, all these variables are free variables. So in this example, we have a set of strings x and y. So, and another query can be a pretty print this expression. It's just a string 2 plus x plus y. So that are so-called queries. And here's the OO style programming. If you are a traditional OO programmer, you may implement this behavior like this. So you define an abstract class exp as a base type with a method called traversals inside. And for each data variant, for variable, for addition, for literals, for these 3 data variants, you need to define 3 classes that extend the base class, and you implement the free variables method inside, respectively. So there is actually boilerplate. As you can see, there are a number of data variants, and for each data variant, you need to define a class, and you need to put this traversal, this method inside. And also, it is extensible on data variants, because if you add a new data variant, for example, if you want to have subtraction in an expression, you can just define a new class, sub extends this exp, and implement the traversal. But on the other hand, it's less extensible on behaviors or operations, because if you want to pretty-print expression, you need to add this method pretty-print to the base abstract class, and add all the cases, add the implementation for all the cases respectively. So it's less extensible in that case. So now we want to avoid such boilerplate code in traversals. And a fact is that sometimes users only focus on the so-called interesting cases, and the interesting cases only account for a small portion of the data variants. And so as you can see, this is the example that I said before. If you want to add new data variant for subtraction, you need to write the code like this, and the method traversals returns a set of strings, and it simply delegates the task to the subnode, and it gets 2 small sets, and it tries to get a union of these 2 sets. And the code is exactly the same as the add before, as you can see, because for add or for sub, we just simply collect the information and gather. So it's the same. And so how to avoid this boilerplate code? Our approach, we introduce the concept of object algebras here. So this concept was proposed in the paper Extensibility for the Masses in ECOP 2012, and it aims at solving the expression problem. So it's a type-safe approach, and it supports 2 dimensions of extensibility. So the 2 dimensions are the extensibility on data variants and on behaviors. So we try to use this approach. And with object algebras, the data structures need to be defined as an object algebra interface. As you can see, the Java code there. So it's the data structure for the expression example, and it's a generic interface with 3 constructors inside: the literals, additions, and the variables. So it's a object algebra interface. And for specific behavior, also the same example, we want to collect the free variables. We need to write code like this. We define an interface that extends the interface, the data structure, exp with the sort instantiated. So the type set of string is the type of the result that we want, because when we have the query, we collect the free variables. We want to get a set of strings. So here we instantiate this sort, and we have the three cases. We have the default implementation in this interface. And this is the traversal code that we usually write. But there's still lots of boilerplate in traversals, because now we have another dimension. We have the other dimension. Before we have the dimension for each data variant. We define a class that's the dimension. That's the dimension of data variants. Now we have the other dimension. We have the dimension of operations. So the question is, can we create a generic traversal for this kind of queries? Because the generic queries is just it takes a syntax tree and it takes a data structure and it returns some result of type T. So if we have this generic query, we can use instantiation. So for free variables, we just instantiate with set of strings. And the solution is to use monoid. Monoid is also a well-known concept in many functional languages, and usually it has two parts. The first part, it contains a value that represents no information. So for example, 0, and also a binary operator, for example, plus, 0 and plus, so that's a monoid. And in our free variables example, we have an empty set that stands for no information, and the binary operator is just a union of two small sets. So it helps to gather the information. And so actually we capture this kind of generic query like this. So it's interface query with the sort that extends exp-alg, and there is a monoid inside. And for the three cases, for the addition case, because we have subnodes, so we do traversals. We use monoid. We use this join function to collect and gather the information. And we have variables, and later for the space cases, we just return nothing. And later on, there is a so-called interesting case for the variables, because we need to collect the full variables. We need to capture the strings. So we only need to override the interesting cases. And as I just said, the interesting cases only account for a small portion. So in that case, a lot of boilerplate code can be avoided. And furthermore, another question is, can we automate it? So can we capture the template for these generic queries and generate the generic traversal code for us automatically? The answer is yes. So finally, in our Shai framework, we use the simple annotation at algebra, and we put this annotation before the object algebra interface, and it generates this interface query, the generic query for us. And now the code that users need to write is only the free vars at the bottom. So the code that user needs to write is much shorter. And that's the design pattern for the queries. And another pattern is the transformations. So transformations simply take a data structure and returns another data structure with some information modified. So here is the pattern that we capture. So we have this generic traversal for transformations. And the idea is to use the identity approach. We have the base algebra inside, and for each case, we simply delegate the task to the base algebra. And whenever we want to do a transformation, we only need to override the cases. An example of this transformation algebra can be doing substitution. So we substitute expressions for variables with a specific name. And here as you can see, we use this generic traversal for transformations. And there's only one interesting case. So for variables, we need to judge whether the names are equal. So, and we return the expression to substitute. And also we have another application that is pipelining transformations. Because the base algebra of this generic transform, the base algebra inside, as you can see, alg, it can also be another transformation algebra. So if we put another transformation algebra here, we get the pipelining transformations. So in this example, as you can see, it's like we have an expression, and we do substitution 3 times, and finally we try to collect the free variables for this new structure. So it's pipelining transformations. And there's more functionality in Shai because in total we capture 4 kinds of design patterns. We have the queries, the transformations, and also the generalized queries and the contextual transformations. I'm not going to present them in detail because there are a lot of examples in the paper. And finally, as I said, we support the annotation at algebra to generate this traversal code for us automatically. And furthermore, another thing is that extensibility is also supported because we use Object Algebras, and it has 2 dimensions of extensibility. So let me recall that. So here we can see for each operation we define an interface. So that's the extensibility on the operations. And the other dimension is we can also do extensible things on data variants. So here we can collect free variables for expressions. But what if we want to add a new data variant? We want to have lambda calculus. We want to have lambdas in the expressions. So we have another object algebra interface, the lam-alg. And in Shai framework, it generates 2 generic queries for us automatically. And since Java supports multiple inheritance for interfaces, so we can define an interface that extends both, and we override some cases. We add the default implementation for the case lam-alg, and finally we can deal with we can collect the free variables for the new data structure with lambdas in expressions. So that's the other dimension of extensibility. And finally, that's the case study of our work. We have a domain-specific language for questionnaires called QL, and this is the code that users write. So it's a form of driver license, and the first question, what's your name, and the input is a string, and what's your age, and the condition statement. So. And we want to use the Shai framework to implement this QL language. And we see how it helps to avoid boilerplate code. And that's the statistics. We have the percentage of overridden cases. So the number in the parentheses represents the number of data variants. So we have 24 data variants in total. And we have a number of operations, and as you can see, the interesting cases that are the cases that we need to override only account for a small portion. So that's the case study, and finally it's the summary. There is a lot of boilerplate in AST traversals, and we capture 4 kinds of design patterns using object algebras to avoid this boilerplate code. And finally, we have a Java library that uses Java annotation for automatic code generation. And this approach is type safe, extensible, and it supports separate compilation. That's all. Thank you.
We do have time for a couple of questions. Anyone? So you're saying you support generic traversal.